Piauí that he founded, that IMPA is the only place in Brazil that starts the conference on time, which is not true, but we have to start on time now, so he cannot be sorry about the statement. It's a pleasure and an honor for me to first present the series of IMPA Magna conferences upon request of its director, Professor César Camacho. The purpose is to bring some of the most outstanding mathematicians of our time to expose their recent work and how it fits their vision of mathematics. The program is financed by private donors. I didn't give you any hint of who, or one of the donors, who could be. We have certainly achieved our objective by initiating it with David Mumford, awarded with the Fields Medal and Wolf Prize. From algebraic geometry and number theory, while he was in Harvard, he first moved to computational vision at Brown, and now to differential geometry. Today, he's talking on geodesic warping of Euclidean space, its dynamics, curvature, and applications. Professor Mumford.
Thank you, Jacob, and thank you, Cesar, for this wonderful invitation. This is, wait a minute, this is too much for my pocket. This is the third time I've been in Rio, and it's very exciting to be here. This is always one of the most exciting mathematical watering places as you wander around the world. You can go to Mumbai, and you can go to Rio, and you can go to Singapore. There's a few, you can go to Istanbul, a few places, but this really is always both the most beautiful, and there's so much energy here. It's wonderful to feel this. So thank you so much for this invitation. I don't think I can do justice to this introduction. You've got someone who's 75 years old, so my latest work, may not be what I got the Fields Medal for, but in any case, I'm enjoying what I'm doing, and I'm going to. There is a group of us that partly in Johns Hopkins, partly in London, partly in Paris, partly at Brown, involved in this activity, and I think there's some very interesting developments coming out of it that younger people may want to get involved in. So I'll talk today, somewhat less technical talk, and then on Wednesday, more getting into the nitty-gritty of infinite dimensional geometry. So, what? No? Doesn't work? Where do I point it? Oh, now it's happened. I was hitting this one, yeah?
You touched the wrong button.
Touched the wrong button, yeah. That's clear. I certainly did. This one, yeah, that's what I thought I was doing. Okay. Oh, good. There we go. So the middle part of the talk will be more mathematical, but I want to start with an informal introduction to the ideas that are involved here, and I will end with some applications. One of them is my most recent passion, this Chinese map, and so I'll explain a little bit about that when I come to it. Okay, so the history really goes back to Durer. I mean, in the time of the Renaissance, the there were some amazing polymaths who both did art, but were serious mathematicians at the same time. I mean, there's Alberti and Brunelleschi and so on in Italy. But Durer, so he published this book. The Latin title is De Symmetria, and the German title Vorbrüche von menschlicher Proportion. So these are illustrations from his book. So he was analyzing the shapes here, clearly, of human faces. And notice what he's doing. He's drawing lines which go through similar parts, features in the face. For instance, over here, you can see that this is on the top of the eyebrows, this line. And here he's particularly getting into the nose and the orientation. He's producing geometric constructions which to try to express the differences in shape. Now, as opposed to perspective geometry, for example, which was also introduced, as I said, by Alberti and other architects and artists, that was taken up by mathematicians. But the idea of looking at proportions of real objects, such as faces, did not lead immediately to any mathematical work. So the next point in our historical survey really is a British biologist, D'Arcy Thompson, who very much in the spirit of Durer took this up in a famous book on growth and form. So this is one of his experiments. So he has the human skull here, and he takes a rectangular grid, and he simply he's tried to deform this grid, in some cases using relatively simple functions, in some cases they're quite complex nonlinear functions, in order to fit various primate skulls here on a dog, which you can see is much more of a deformation. If you look closely, you'll see that it doesn't match exactly, which is also a theme here when you're making a match of this kind, that you need to find matches which give the sort of overall distortion at a certain scale. Now, continuing, so all right, you can ask yourself, what is the appropriate mathematical theory for coming to grips with these questions? So essentially, it's a question of solids or fluids. Now, in many ways, it may be actually more natural to think of this as these being deformations of a solid, but elasticity theory and fluid motion are completely different theories, in the sense that in elasticity theory, every point remains, it knows where it came from. So it's like people migrating around the world speaking their mother tongue. They know where they came from. Whereas in a fluid, once you mix it up, no one remembers where they came from. But in any case, there's sort of two quite different mathematical tools. They've both been developed in recent times for this kind of question. But the fluid part, surprisingly enough, leads to some of the most interesting mathematical theories at this point, at least. So just to set the stage, I introduced one equation, Euler's equation. So this is the equation that governs incompressible and non-viscous fluids. So water is very low viscosity and is almost completely incompressible. And Euler's equation is this one. So at any point in space and time, you ask, where's the fluid moving at this point, at that instant of time? That's going to be a vector, which is the fluid velocity at that point. It doesn't say where it came from, notice it. It's just at that point. And now, Euler's equation says the acceleration, so we're mass is constant here, density is constant. So we have the time derivative of velocity, and this term simply says the velocity is carried along by itself. So you have a bit of fluid moving like this. It tends to retain the same velocity, and it will move in the direction in which it's pointed. So this is the direction it's pointing, and then its derivative in that plus the time derivative, that essentially says that fluid that amount of water right there is going to be moving in the same direction after a little bit of time, although it'll be at a new place. But that's not entirely true because there's pressure here. And pressure is the force. So the gradient of pressure gives you an acceleration of the fluid. And the fluid has to be incompressible. To be incompressible, the divergence of that vector field has to be 0. So this was Euler's equation, and there have been infinitely many studies of this, but it remains a very difficult equation. Okay, now the next point in our history was this tremendous work by Vladimir Arnold, who was here actually. Well, I sat with him with Jacob on the International Mathematical Union for many years, so I got to know him quite well, and his very strong and remarkable personality. But this is one of his first pieces of work. I do have font problems. Oh, yeah, okay. On the differential geometry of Lie groups of infinite dimension and its applications to the hydrodynamic of perfect fluids. So what he said was that previous equation had a geometric meaning. And this geometric meaning was that it was, if you considered the entire universe of all incompressible motions of the fluid, volume-preserving motions of the fluid to another place, this would be a geodesic through that infinite dimensional group. And so if you take the phi as a motion from a point x to a new point, phi of x, depending on time. So this is a time-varying diffeomorphism, a motion of the fluid. And you ask, is this a possible motion for an incompressible fluid? First of all, it has to be incompressible. That's that S. But his point was that this equation here that says that the motion of the fluid is given by that velocity is a geodesic if you defined the metric, the size of the velocity field as being just the L2 norm. This is supposed to be R, but I always have some font problems. Okay. So this was a tremendous link between fluids that set it up and connected it to geometry. Now, in the meantime, let's go back to this study of faces. The statisticians got involved. So here's a skull. They have names, these points on a skull, the gonion and menton and sella and nason. So people have measured tremendous number of skulls. And so you would like to, a statistician wants to do statistics. So you'd like to know how to describe shapes in space. And now classical statistics deals with vectors of real numbers, not with shapes. So various people tried to attack this. Kendall introduced a method of dealing with points in the plane, modulo translations, scaling, and rotations. And if you think about it, translations put the center of gravity at the origin, and scalings and rotations amount to multiplying by a complex number if you consider R2 as being the complex plane. So here's the description of all triangles on a sphere, which is the complex line. So the equilateral triangle at the pole, degenerate triangles along the equator here, and they flip over in the southern hemisphere. Bookstein, what he introduced was how do we go into, from landmark points, so these are called landmark points. He studied here, these are mean age 8 females. He found the average face using this kind of technique, but he interpolates the deformation from one face to another using methods from analysis. So this is going to be the theme of what we want to talk about. So the next step was really the person who I admire tremendously, who's introduced a tremendous number of radically new ideas into statistics, my Swedish colleague, now retired, Ulf Grunander. And he had this idea that medical imaging was just coming into fashion, becoming available, I should say, in the 90s. And his idea was we should clearly have a template human body, or several of them, depending on age and gender. And the way we should look at a medical scan was to compare that scan with the template and see what was characteristically different. So we'll see at the very end of the talk some examples of recent work in this direction. So he wanted to warp full 3D MRIs from the patient to a template human. And his idea was to use a fluid-type model. So what you tried to do was to match the two in such a way that in the matching, the kinetic energy of the deformation, well, that something was minimized. Something was the best possible matching. And so his idea was to replace Arnold's. So Arnold had this norm for vector fields. That doesn't work if you don't have volume preserving. It totally messes up. You have to use higher derivatives of the velocity field. So you put this differential operator in here. It has the effect that you're looking for velocities which are not just small velocities but have small derivatives of low order, as well as just the size of the velocity. So you minimize this as you're warping one human image into another. All right, so that's my historical survey. Yeah, I see what. Yeah, I knew there was going to be a font. The font problem. This box is always going to be R for the Euclidean space. Yeah, okay. There was a missing font. Oh gosh, there's another one. This is supposed to be a script L. Yeah. I had a. Oh, yeah. Maybe we should go back to the PDF. I guess we can. So now we go to some geometry. So the simplest way is, let's look at a nice finite dimensional manifold that we're going to take to be n tuples of points in Euclidean little n space. So this is a configuration of points, like we had the 4 points on the skull in the previous slide. The totality of these n tuples of points forms a space, it should be script L, which of course has dimension capital N times little n. Now the tangent space here, if you're going to move the n tuple, it just amounts to moving each of the points with a vector v. So the basic idea is how are we going to measure distances from one configuration of points to another? Now, the right way to do it, I think, is really that what you want is to think of the motion of the points as being the values of a motion of the entire space around them. So you're moving the whole ambient space, and that is warping the landscape points. And you seek the vector field of the whole of the space, which minimizes this norm we introduced, which, as I say, it just penalizes the derivatives of v and its value. Now, the mathematics of this is all based on the Green's function of this. So the Green's function is a kernel. It's this differential operator is usually translation invariant, and the kernel is just a function of the distance apart. So this kernel typically is going to be just sort of like a Gaussian function of the distance between x and y. And this is mathematically the keystone to the analysis. And so you have a problem of constrained optimization. You want to minimize the size of the big vector field so that the value at these points is given. So this becomes a simple problem in calculus of variations. How do you find a vector field of smallest norm with given values at those points? And it's easily solved using this Green's function. I just run through this. The idea of Lagrange multipliers is going to tell you that at the minimum, you see, Lagrange multipliers say that the derivative of this function should be the derivative of this function and times a multiple. And what that amounts to saying is that L times the vector field should be a multiple of the delta functions. So if the vector field, if you hit it with a differential operator and you get delta functions, that means the vector field is the sum of the Green's functions. That's it. You just apply k to both sides, and it means that gives you v back. And so v is a combination of the Green's functions at those points. So you work it through, and these play the role of momentum. So what happens in this situation is you have velocities, the v's, and then you have the momenta, and you get from the momenta to the velocities through the Green's kernel. And so this is it's simple to understand. If you're going to move these points in a certain way, you think of one point having this desire to go in a certain direction, but it's sitting in this fluid, and it can't just move by itself. It drags its neighbors along. So if that point B wants to move, depending on the distance from A to B, the other points move with it. And so the velocities of the points are given by the momenta coming from all the nearby points. So this is basic mechanics, and you get back the momentum from the velocity with the inverse matrix of that guy. And so now we know now we have Riemannian geometry. What we can assign the length of the vector field given simply by its values at the points. It comes from minimizing this, and you just substitute this value for the global vector field, and you find that the inverse of k gives you the matrix G, the tensor for the Riemannian geometry. So anyway, and then you can use Hamiltonian equations to find out how things move. So the point P, its motion, which is VA, is just the average of the momenta in nearby points. And this is the acceleration here. This is the force term. And I think it's, rather than explain it, this picture will illustrate it. So now we get back to, now you'll see what I'm talking about. It's quite straightforward. Suppose you want to move those 2 points to these 2 points, but they're sitting in this ambient space, and they're dragging the ambient space with them. So as they move, a grid goes like this, and it's not in the least bit volume preserving. It's really concentrating everything before it. Now, why don't they go in straight lines? Well, that's very simple. If they're moving in the same direction, it'll be a lot cheaper to get onto the same bus and take the same bus from here to there, because then the total velocity with which everything is moving, if you're on the same bus, you don't have to drag nearly as much with you as if you have 2 buses. You have to burn more fuel if you've got 2 buses. Whereas if you're going in the opposite direction, here this point is moving there and this point is moving there, you want to get far apart, because if you're close to each other, you'll get a tremendous shear in the middle, and that'll produce a big derivative in the vector field. So you want to avoid each other if you're moving in opposite directions. So you see, this has interesting effects, this simple idea of what are the geodesics in this landmark space. And here's an example from the thesis of my student, Mario Michelli, who's done a lot of work on this, and on Wednesday I'll talk about some other work of his. He started with those 4 points, which are the solid dots, that one, that one, that one, and that one. And they're supposed to move to those places. So they do a remarkable dance, you see. So the point is, this one wants to go here. So this one veers away in order to avoid this one that's moving. Now, this one wants to go down here, but the problem is this one is moving this way. Since it's going down instead of up, it goes away from there. And this one does an interesting dance. At first, this one moving up and this one over here pull this towards it, and it makes a little loop. Anyway, there's an amazing dance. It creates a set of landmark points like this does crazy sort of dances in this metric. So I don't know. I think this is a wonderful metric and a nice finite dimensional space. Here's another thing that it can do. The equations are a lot like planetary motion. So if you have 2 points here, and their initial velocities are like that, it turns out that they capture each other, and they do a sort of a death spiral in and in around each other. Whereas if they do the same thing, but they have a slightly greater momentum at the beginning, then they come towards each other, and it goes as far as this, and then it spins out again. So the 2 spin around each other for a little bit, and then they fly off. So one of the points of particular interest is to understand curvature in this manifold, which dominates how geometry works. And this curvature is very important when you're going to warp one human body to another, because if the curvature is positive, geodesics are not unique, and you're going to have trouble. And the curvature is negative, then it's the whole geodesics become quite unstable. So the curvature is a key player in the applications of these ideas. Okay, now, what? Okay, how am I doing time-wise? Okay, this is good. I want to spend a little while relating this to Arnold, because, as I say, he's now has passed on, but his work was, he was exactly my age, actually, and so he's an important figure in my life. So there is a bigger perspective to all of this, which is quite beautiful, having to do with what are called Riemannian submersions. So I'll describe this. So if we take all, oh my God, how did that get to be a P? That was supposed to be R. Okay, so this is Euclidean n space, and we're looking at all the diffeomorphisms, the one-to-one continuous maps with derivatives of Euclidean space to itself, becoming closer and closer to the identity when it's far away from the origin. Anyway, it's an infinite dimensional Lie group. And what's its Lie algebra? Well, if you have a motion of the space and you perturb it a little bit, that just means you have a vector field. So a perturbation, if you start with the identity map x to x and you perturb it a little bit, you just add epsilon times the vector field, and that's in the tangent space at the identity to the diffeomorphism group. On the other hand, suppose it's a group. So I can move from the identity to another point by right translation, and therefore its derivative, its differential, is a map of this tangent space to this tangent space. Well, all that means is that you first use the phi because it's on the right. So now the new motion, you just replace x by phi of x. The new motion takes phi of x to phi of x plus epsilon v of phi of x. So that's just the way fluids work. It means that v, if we use right translation, we're measuring the motions in this group the way people always measure fluids, by the velocity with which a point phi of x is moving at whatever time you're dealing with. So you see, we have a very beautiful mathematical setup. We're dealing with geodesics on a Lie group with respect to a metric which is generated by the group from an inner product on its Lie algebra, on the tangent space of the origin. And then the length of a path, this is what fluid people call the Eulerian form. If you have a path, then you have its, at any time t, you have its t derivative is given by a vector field, and then the length of that path is just integrating the length of the path at each point in time. And that gives you the path. Okay, now, this is supposed to be the script L, the landmark space. All right, so now, this is an R. So the point is, I have the group of all motions of the space acts, of course, on n tuples, right? I can take a diffeomorphism and take that n tuple to a new n tuple. So if you choose a base n tuple to start with, I get a mapping from diffeomorphisms to n tuples by acting by phi on this n tuple. So we have a natural map from the diffeomorphisms to this coset space of n tuples. Now, what we did before, choosing the vector field to have the least norm, what it amounts to is that you have a norm on the whole diffeomorphism group. Now, whenever you have, and what it amounts to is you have a submersion. What that means is this: you have a space here, and let's say it maps to a space down here. Well, in that case, each point here has an inverse image. It's fiber. So the tangent space here has a vertical part, and using the inner product, it has a horizontal part. And a submersion just means that the metric on the horizontal part is what the metric is down here. So it means that you get the metric on this quotient space by taking the vector upstairs, which has small as norm, which would project to that, which is just what we did. So now there's a whole theory of these Riemannian submersions, which is really very nice. And it says that the geodesics down here are going to be geodesics up here in the big space, which are horizontal. If they're tangent at one place, they're perpendicular to the fibers at one place, and then they will automatically remain perpendicular. Now, Arnold, in this beautiful paper, worked out the general theory of what geodesics in such right invariant metrics are. So he produced a completely general formula, which is extremely simple and beautiful. This is the metric on your vector fields. Let's say this is your Lie bracket, and what you do is you just take the adjoint with respect of the Lie bracket with respect to the metric, and you call that add star, and then the geodesic equation looks like this. All geodesic equations, this will be a velocity, so this is an acceleration, and it'll be a quadratic term in the velocity. So it's your standard sort of equation. All right, and I just mentioned that then this is sort of a criticism, actually, of mathematical physicists and of applied mathematicians. They, I think sometimes they're obsessed with the idea that they have to always have equations which have physical relevance. And so the history is sort of interesting. All these people who worked with Arnold, Kazin and Jerry Marsden, and who worked in similar topics, they developed his theories in many directions, but they stuck to equations which had physical relevance. Suddenly, out of a crazy direction, medical imaging and MRI scans of the body, Ulf Grenander and Michael Miller say, let's look at these equations. We drop volume preserving, and we know it's going to collapse unless we put those higher derivatives in. Putting those higher derivatives in makes the equation completely physically is in another universe. It doesn't make any sense physically. So they never looked at these equations. But I think this was a whole rich area, was to look at Arnold's equations in these settings which weren't really physically meaningful. So you have this L, which involves derivatives. And so you have a momentum which is different from the velocity. And applying the differential operator gives you a momentum, and applying the Green's function kernel gives you back the velocity. So they're dual to each other. But the point is, this tends to be smoothing, and so the velocity can be quite smooth, even though the momentum is highly singular and has delta functions in it. So the idea of looking at fluid equations where you have momentum which is delta functions had never come up before. And unfortunately, the equation got messier. The geodesic equation, when you work it out, you see the bit of Euler's equation. If u equals v, then these two terms were the same in Euler's equation. This would vanish. This would actually become the gradient of pressure. So it's more complicated. And when you do take this to be delta functions, you get those pictures I drew earlier. Okay, now I want to say a few words about the connection to Euler's equation. It seemed as if it was in another area. So the way Costas de Fermat explained it to me, the problem with Euler's equation is that there are so few things you can do with it. You can't manipulate it. It's brittle, is the adjective he used, Euler's equation. So the standard method that people use for, well, of course, but the standard method is to go to the Navier-Stokes equation and introduce viscosity, which regularizes the equation to a great extent, and look at Euler's equation as being the limiting case when the viscosity gets small. But here's another way of looking at Euler's equation. Take your measure of the size of the vector field to be Arnold's size. That's just the plane L2 norm. Now that wouldn't work, but if you add the square of the divergence times a constant, it does work, and you can apply this landmark space theory, and And then you let this go to infinity. Now, if that goes to infinity, that means that not being volume preserving is more and more painful, and you pay more and more money to violate volume preservingness. And so you let it go to infinity, and lo and behold, it will approach the Euler's equation. Once it goes to infinity, you'll get back Euler's equation. So this equation has a interesting form. The kernel, the Green's function, has a highly singular Green's function. This is the Green's function of the identity minus the Laplacian, and you have to take the second derivative of that, which puts you right on the edge of kernels, which you can make sense of. It's called the Calderon-Zygmunt kernel. But in any case, it works, and it does indeed. So these are two simulations of fluid flow using landmark space theory. So I've taken a single landmark, which is somewhere in here, that's shooting along. So you imagine a bit of water, and you're firing a gun into that water, and this is what the water does at a certain time. This is just my simulation on the computer. It preserved areas to within 7%. But in any case, I just wanted to see with my own hands. I mean, I like to calculate. I love MATLAB, actually. It's my favorite tool. And you can really see volume area preserving maps coming out of landmark theory, which seeing is believing. Here's after even more time. My simulation is not so great. It's 4 times more than this, so it's only 25% area preserving. Clearly, if I had a more powerful computer, it'd be better. But you can see what's happening. You see, it's developing these characteristic vortices, which are typical of if you have a high velocity thing going through some fluid, you get these so-called vortex streets are produced, and you see these vortices beginning to develop. Should really have a bigger computer, and maybe you'll get the whole mess of the vortices on vortices coming out. But in any case, as I say, it's instead of worrying about the zero viscosity limit, it's a limit in which a small amount of compressibility is allowed, and then you force that to go to zero. So my dream would be that this new approach to Euler's equation might give some insight. It's actually not the Clay Prize, which is for the Navier-Stokes, the incompressible Navier-Stokes equation. I don't know why they chose that one instead of. But even for Euler's equation, I don't know. I think smart money says it probably. The question is this: if we start with some fluid flow, in the Euler case, can you continue to integrate it for an infinite amount of time, or does it develop singularities which blow up? So the vorticity goes to infinity, and at that point it ceases to be a smooth solution. So this is the unknown, and many people worked on this, and it's I don't know. I sort of think smart money says it's probably singularities do develop, but I don't know. I haven't. People don't say that sort of thing in print. But whereas with the Navier-Stokes, I think smart money thinks that solutions should exist for all time because the viscosity term regularizes it so much. But in any case, if we go back, you could see how because of this sort of behavior, you can see that nasty vorticity type effects come out of these equations in a very natural way. Okay. So now let me talk a little bit about applications here. So as I mentioned, Michael Miller was one of the the first collaborators who worked with Alcrinander on this procedure. And he then founded a group, which is now at Johns Hopkins. Laurent Younes and many others have joined him. And there is a nationwide group in the U.S. called BERN, the Brain Informatics Research Community, which is studying the problem of warping different medical scans to templates and analyzing from large databases what are the features that characterize things. So, for instance, the cortex has been one of the main areas that people have a huge database. Well, BERN, the brain. But in particular, can you diagnose symptoms of Alzheimer's, schizophrenia, and fetal alcohol syndrome are three of the diseases that have been much studied here. And there are, at this point, very large databases. So, for instance, their group, the Hopkins group, worked very hard. There's a structure in your brain which sits on both sides called the hippocampus. It curls behind your ears, which is the seat of formation of memory. It's not so much that your memory is stored in the hippocampus, but it's absolutely crucial for the formation of new memories. And it's known that it kind of shrivels up in a nasty kind of way if you have Alzheimer's. So they used these medical scans, and they used exactly this technique of geodesics. Their method was this, actually. They would take a database of normal individuals and abnormal individuals, and then they would find a sort of a mean normal individual. So that would be a scan so that the sum of the squares of the lengths of the geodesics to all the samples is minimized. So that would be the mean normal, and then they'd have a mean abnormal, and now they'd take the geodesic from the mean normal to the mean abnormal, and they'd try to find, through the warping of one to the other, what was the biggest change that took place. So it was a very systematic statistical approach to identifying critical features. Now, so preparing for this talk, I went to see what their latest work was, and so they have a beautiful paper. See, the problem with the brain is it's also there are only certain features which really you can clearly identify between two individuals. The problem is that, of course, the brain folds. Yeah, let's go on. Yeah, okay. So the brain folds. So you see here the white matter and the gray matter. This is a cross section of a normal brain. This is the abnormal brain. And what's happened here essentially is that the white matter has degenerated and the ventricles have enlarged tremendously. And now, if you look here, the details of the gray matter here, what's called the tertiary folds are very variable between people. So you have to have an error term. You don't want to have a geodesic that goes exactly from one to the other. That would get terrible results, because the fact of the matter is that there are individual changes which seem pretty random. So you want to get it close, but you want to get the right things close. So what they proposed to do was to use the sulci and the gyri. The sulcus is a groove in the brain, and the gyrus is a part that shows on the surface of the brain. They use the whole brain surface, and they actually use the full MRI image, and they do a 3D warping. Now this is just a 2D slice of a 3D warping, and this here shows how far things moved. So you can see that the ventricles enlarged tremendously, for instance. Now, this is an indication. So here, you see the kinds of things that you deal with. Here, this is not very clear. You can see it too clearly. But here, simply an optimal affine matching between the brains has been made. These are three views of the brain, and the different strands here are sulci and gyri in different individuals. And this is after trying to put them together in a standard brain. And you can see that you can't get them to match by affine maps very well. Now here's just when you're doing the warping on the image itself, and here you're doing the warping together with the sulci, the gyri, the surface, and the image. And you can see that they're much more successful in actually aligning all the branes with each other. So these are the principal, it's probably the principal sulcus between your frontal areas and your posterior areas. And this, so this is the comparison of the algorithms of increasing effectiveness. Okay, well now I want to get to the part which was my own passion lately. Getting older, this amazing thing happens to you, which is you realize you yourself have seen so much history that younger people can't believe. I heard the Beatles when they first came out. I remember when algebraic topology was just in its infancy, and it was Eilenberg MacLane spaces. I mean, all this stuff was the latest things when I knew Grotnik and so on. So you've seen history, right? Well, you can go further back. So I talked to a lot of my Indian friends about the history of Indian math, and then I got interested in China. Now, what's this? This is actually a rubbing from a piece of stone that's about 1 meter by 1 meter, and it's in the city of Xi'an. It was carved in the year 1136, and these lines, these are not superimposed by some modern person to help look at this map. These were carved in the stone. Now, what is it? You see, here's the coastline, like that, of China. This is the Yangtze River, like that. This is the Yellow River. Goes up into Inner Mongolia, out to the mountains. This is China. And the thing which every historian says about this map, they say, oh my God, this is so accurate. Look at the shape of the Yellow River. This is the right shape. But no one, the point is, no one could quantify what do they mean by saying this is accurate. Well, obviously, what they need is warping. Why stick to MRIs? Let's take maps. If you warp a map to another, it's known by geographers as georeferencing. And they georeference by various sorts of splines. But I think this is basically, it's not the right tool. I think that the methods of landmark geodesics are the right tools for warping this sort of a situation. Now, the reason why this is particularly interesting is that it asserts up here, this is the legend of the map up there, it asserts up there that these vertical and horizontal lines are exactly 100 li apart, which amounts to, I think if I'm right, it's, if I remember, it's like 30 kilometers. They're about 30 kilometers apart. And there's more than 70 of them each direction. Now, down here is actually Hanoi, is on the map here. Up here, this is Inner Mongolia. This is desert up here. So it goes quite a distance from north to south. Now, we know the Earth is not flat. These north-south lines cannot possibly be equally spaced up here and up here. And in fact, if you take the cosine of the latitudes, which from today, we see that they should be, they would be about 3/4 the space of distance apart if you go along vertical meridians, north-south meridians, as they would be in the bottom of the map. So the question is, what was happening here? How did the Chinese look at this? So the point is that there was a long tradition of the Chinese mapping the Earth as a flat object. Now, there were people who speculated about cosmology, and there was a vague idea that the Earth was like an egg floating, or rather, they talk about the Earth being a yolk inside an egg, which was the universe containing the stars and the planets. but these were always, there was nothing, there are no numbers attached to this, and in some reconstructions, I mean, the Earth turns out to be about 20 times as big as it really is in these. So these were never connected to actual practice. On the other hand, these maps were hugely important. They were continuously fighting the people on the periphery of China from the beginning of time, more or less. They're fighting the people outside the kingdom of heaven where they were living. And in fact, Cartesian coordinates were proposed by this man, Pei Shui, around 250, just after the Han Dynasty, and probably were introduced in the Han Dynasty. Now, the question is, how could they possibly have sustained this philosophical belief through the Song Dynasty, through the 12th and 13th centuries? And there's a particular figure, a great genius, Shen Kuo, who loved math. He led military expeditions. He was a high mandarin. He became one of the emperor's principal advisors, but he fell victim to palace intrigue because his group was proposing reforms and other people didn't like the reforms. The usual sort of politics as usual. And he was disgraced. And when he was disgraced, he produced a map of China in 30 panels, his magnum opus, which is lost. However, this map was made just one generation afterwards, after the fall of northern China to these Manchurian invaders. So the question is, how accurate is the map? So we took 40 landmarks, right, on it that we could identify precisely on modern maps. And so naturally we cranked out the algorithm. And that's what happens. So if you put this in true longitude and latitude coordinates, what you find is that the grid looks sort of like this. So the fact was that the east-west lines were quite accurate. And that's one of the real curiosities of the story, is that ever since the early Han Dynasty, they had been measuring north-south distances by the shadow of the sun at noon and the summer solstice, or whichever solstice, or the winter solstice, doesn't matter. So they take the length of the shadow, and so they knew a proper way to measure latitude. So that's a perfectly fine way to measure latitude. But they didn't interpret these things the way Eratosthenes did. So they had quite accurate measurements, and in the Tang Dynasty they refined these. So you can see that the east-west lines are really quite good. So they must have been using this shadow method. Their information out here, this is Yunnan province, is sort of sparse. So we couldn't find any landmarks here that we could really identify. This one is this bend in the Yangtze River. And up here they had pretty good data. This was their Silk Road, goes up there. But you can see how it's all distorted. The points really have to be pushed way out here to find their proper position. So finally, let me finish by showing you this. So here we've taken the actual map and warped it, and the white is the map, and the yellow is the modern river. Now this, for instance, this is the Yellow River. The Yellow River did indeed. This whole place in here is completely flat, and every century or so there's some humongous flood, and the Yellow River completely changes its course and kills several million people. This has been a perennial problem in every dynasty. So, but you can see it's pretty good here. They didn't trace it quite so far out. I think their map ends here, and this is the modern continuation. Here's the Yangtze River, and they didn't have this bend quite right. I think this is very mountainous back here, and clearly was hard to get. I think the inaccuracies were most striking along the coastline here, where they're as much as 20 degrees off the real trend of the coast, and they must have known that the map was wrong. It just seems incredible they didn't. So, this is Hainan Island, which is pretty far off, and always in here. There's a mysterious river that Confucius mentioned, so it always has to be there. It's sort of like where this is the Mekong, where the Mekong is, but no one not really there either. This was not well explored, the Burmese border. So it's, to me, the most interesting thing is this difference in cultures, that a culture can be so strong that a scientific principle like the roundness of the Earth is actually just rejected by the mainstream conservative people. I mean, one of the problems was that the imperial exam, which qualified you to be a Mandarin, included only the most meager science and math. I mean, the main emphasis of the exam was to write poetry and know everything that Confucius said. So it was, but in any case, it's sort of, I got carried away by the history. So sorry to end the talk with a history lesson, but I found it such a beautiful application of abstract math. Thank you.
So I want to open the floor for comments or questions. Please.
Yes, I have a question. I'm intrigued when you mentioned about vortex streets and so on that image you were deforming. Yeah. So when you had the vortex street there, you were still dealing with Euler's equation?
I'm dealing with the approximation of Euler's equation given by, actually, I make two simplifications. I first introduce a small amount of compressibility, and secondly, I compose the operator L with a really strong regularizing operator, which has
those G's,
very small higher order terms, so that.
So that adds some friction term, though, because Euler's equation without viscosity would not generate, right? So that probably, in this approximation, would be some friction term must be coming in. Because Euler's equation without, if you shoot something into Euler's equation, it will not generate vorticity.
No, but it's got infinite vorticity at the point itself, which the point has become a bit of a blob, actually, but that's sort of the effect of my regularization. So it's kind of like a blob going in there. So and I think you have infinite vorticity right at the point. You have two opposing sort of delta vorticities, which...
maybe a related question is when you add those functions, those Gaussians and so on, that sort of rings a bell a little bit with computational fluid dynamics when you do particle methods with radial basis functions. Is that correct?
I don't know. I haven't looked at that approach to it.
Because people actually do that numerically. Instead of deal particle with particle, they put they station a Gaussian function or radial basis function on top of it, and then move that along, and it drags neighbors. Just as you said.
I'd really appreciate. You're giving me some references. That sounds quite interesting.
Well,
thank you. I'm getting into this with quite a naive.
Well, thank you. Thank you.
Can you go back to the slide of the Arnold-Euler equation? Yes. And do you know that there exists solution?
Yeah, we know. Yeah. It depends very much on the nature of the operator L and the corresponding Green's function. Okay, so several things. If L has roughly n over 2 derivatives, or n derivatives, because you integrate by parts, in other words, the corresponding inner product would have n over 2 derivatives, then it's very easy to get global solutions to this. This is very strongly, you see, the point is the V is so much smoother than the U in this situation because of that K there. And it's basically an ODE. And you can solve it like an ODE. So that now, if you get to this thing, which is the one of interest, this is harder to solve, but I proved it has local solutions. Although like Euler's equation, I don't know it has global solutions.
In which, you mean smooth solution?
Yeah, smooth solution. Yeah, starting with smooth initial data, it has local solutions. You're skeptical.
Okay.
More comments? Yes.
Hi. I'm happy surprised to see that your work intersects with that of some people I know well. Sorry. I see that you spoke about the features, and I remember that two friends of mine started getting involved with the Royal College of Surgeons in the study of faces. They started doing it via the study of, because they have done a lot of work on the space of oriented lines in R3 and deriving several structures there. And I think the reason why they were studying it is because the surgeons are very interested in predicting things like different diseases, sort of like the cleft palate, which is related to epilepsy. And I can't remember if it's this part of the body and then the kidneys and the heart that grow together in the beginning, in the initial stage of the fetus. So then later on, these parts have, so to speak, information about each other. So I think that's how they started, and they are trying to like discretize things like curvature and stuff from differential geometry, which is the approach is orthogonal to yours, so to speak.
Well, that's so interesting. One of the things which the Hopkins group and also Darrell Holm in London has gotten involved in this is looking at not just single shapes, warping them, but also you might think of them as shapes in space-time. So you have the actual evolving fetus or body at a certain age, and they try to model that evolution and find, again, templates. They can compare an abnormal evolution to a normal one. So, and this is, it's an exciting direction, definitely.
Okay, let's thank David Mumford. Let me remind you that he's coming back here on Wednesday to talk about life in infinite dimension. Many possibilities.